In this video, we're going to look at trigonometric substitution, and in particular, we're going to look at for integration problems that involve square roots of a sum or a difference of two squares. So we're going to start out with a little bit of warm-up with our trig. So I am asked to write each one of these as a trig, as a single trigonometric function. So the first thing I'm going to do is factor out of 4. The reason being is that if I factor out of 4, then I'm going to get 1 minus the sine squared, which is equivalent to, by the Pythagorean identities, cosine squared. So there's that. Same thing here. I'm going to factor out a 9, leaving me secant squared of theta minus 1, which is equal to 9 the tangent squared of theta. Similarly, I'm going to factor out an a squared, and that leaves me 1 plus the tangent squared of theta, which is equal to the secant squared of theta. Now, if you're thinking, where am I getting all this information from? Well, it is coming from that trig formula sheet that I give you for every single test, and you all should have copies of at this point. My last one is the hyperbolic cosine squared, so I'm going to go ahead and factor out a 16, leaving me the hyperbolic cosine squared of theta minus 1, which is equal to the hyperbolic cosine squared of theta. Now, we need this skill, being able to recognize when to use the Pythagorean identities for trigonometric functions. So that's why it's here. And the other skill that we may need is completing the square. So if I'm asked to complete the square, the first thing I'm going to do is factor out an 4 off the x squared and off of the x. I'm also going to just move that 1 to the side there because I'm completing the square on the variables, not on that constant. So then what I do is I like to take x squared minus x, and then I would do this plus this something. I have to figure out what I need to do to add to x squared minus x to make it a perfect square trinomial so I can factor it as a complete square. Now, because of the fact that I have added this blank, I also have actually added 4 times that blank. And so I need to balance this, so I need to subtract off 4 by that blank. The way I figure out what I need to do to complete the square is I take this middle term, which is negative x, and I divide by 2x. And you're asking me why? Why 2x? Well, I'll explain in just a moment. And when I do that, I get negative 1/2. Well, that's what's going to go here. Negative 1/2 the quantity squared and negative 1/2 the quantity squared here. Now, the reason I use both a 2 and an x is if I think about a perfect square trinomial, I have a squared plus 2ab plus b squared. This came from a plus b, the quantity squared. Now, the only difference between a plus and a minus here is if this is a squared minus 2ab, then I should have an a minus b on my factored form. So you can see structurally I have both a 2 and an a. So the a is this variable, and I have 2a. So this middle term always needs to be 2a multiplied by whatever b is. And then if I divide this by 2a, I'm going to get b. And then if I square it, I'm going to have b squared right there. So that's why I do that in my own little craziness. So this then becomes 4x minus, and this value right here before I squared is what's going to go here. That's why it's a minus 1/2, the quantity squared. And then I have plus 1 and then minus. Now, 1/2 squared is 4 multiplied by 4, which gives me 1. And so I end up with 4x minus 1/2 the quantity squared. And you're like, well, why didn't I just do that in the first place? Well, sometimes I don't always see it. And also, here's the deal. If I see that this becomes 2x minus 1 and then 2x minus 1, which is basically the same thing. So this is the same thing. This is 2x minus 1, the quantity squared, which is kind of a perfect square. If we're thinking about a perfect square trinomial, we do kind of like to have the coefficient on the x being 1 if we're in the land of conics. So if I were to factor out 2, so it'd be 2 multiplied by x minus 1/2, the quantity squared, this does give me 4x minus 1/2, the quantity squared, which matches where I was to begin with. Just side noting. You're like, what, couldn't I have done that? Yep, I could. I did, but I wanted to start out with completing the square the other way. Now, let's come back here and do the next one. Similarly, I am going to write this as 2x squared minus 4x plus some blank plus 3 minus 2 multiplied by some blank. Because remember, if this coefficient is 2, it's really 2x squared minus 8x, and then 2 is going to be multiplied by this blank, so then I have to take off that 2 by that multiplication. Again, I like to take this negative 4x, I like to divide by 2x, because my middle term is always going to be 2 times my variable, my first variable that I see, which is the x squared. This gives me negative 2. This is the value that's going to go here when I square it. And so this is going to factor into 2. I have x minus 2, the quantity squared, plus 3. And then I have negative 2 squared, which is 4, multiplied by a negative 2, which gives me negative 8. So I have 2, x minus 2, the quantity squared, minus 5. And there it is, factored with by completing the squared. Very last one here, I'm going to pull out a negative off the x squared, and that makes it positive 2x. Goes from negative x squared to a positive 2x plus, don't forget my blank, plus 4 minus 1, because this is a minus 1 right here. So this is a minus 1 right here, so it needs to be a minus 1 here. If I were to distribute the negative 1 through, there would be a negative 1 multiplied by this blank, and so that's why it is a negative 1 here, and that actually needs to be positive because I need to do the opposite to balance. And once again, I take 2x, I divide by 2x, I get just 1. That's what I'm going to put here when I square it. That's what I'm going to put here when I square it. So this factors into a negative, and I have x plus 1, the quantity squared, plus, and then I'm going to have 4 plus 1, which is 5. And that's it. Now, we are now going to look at this a squared minus x squared, or a squared plus x squared, or x squared minus a squared. The reason I did the completing the square is there's going to be times where I'm going to need to complete the square to make it match what I expect it to look like. So I may have to have x squared minus an a squared, an x squared, an a squared plus an x squared, or any of these combinations. One of the ways that I can do the trigonometric substitution is this kind of looks like, if I look at my trig formula sheet, this kind of looks like one of the sides, right? And so if I were to look at the way that I defined x, y, and r in my pre-calculus 2 class, I would have said here's x, here's y, here's r, and we know x squared plus y squared is equal to r squared all day long. Now, because of the fact that I had this a squared minus x squared, this looks like if I were to have solved for y, this would be plus and minus the square root of r squared minus x squared. So if I let x equal the a sine theta, and I have a squared minus x squared, and the x squared can be replaced with a sine theta, then I would have the a squared minus a squared sine squared theta, and I'd end up eventually, when I get done, a cosine theta. Now, if you're like, man, that's a whole bunch of trig, how am I going to make this easier? Well, we can always do it by setting up the triangle. It doesn't matter where you put x. You could put x right here, or you could put x down here. And what I mean by this is I can make this x, and I can make this a square root of a squared minus x squared. It doesn't really matter when you set it up. What I do know, if I see a squared minus x squared, the square root of it, then that means I basically have the radius minus the x squared. Just like when I'm, again, going back to x squared plus y squared is equal to r squared all day long, then this is the same thing as solving for y, plus or minus, but we're only going to focus in on the positive because we like to be positive. So it doesn't matter how you set it up, right? You could say that x will always be this one My number that's going to be given to me is always going to be this one, and my y will always be this one. It doesn't matter how you set it up. And you're going to see me here in a minute. I'm going to set it up in different ways, and you choose the one that makes you the happiest. So let's go ahead and do these trig substitutions. Now, I see I have a number minus x squared. This, and it's underneath the square root. This screams to me trig sub, trig sub, trig sub. Cool. So the first thing I like to do is I like to set up my triangle. And I'm going to put theta right here. I know that I have a number squared minus a variable. So this number squared, it must be in the r position. So this must be the square root of 4, which is 2. I can put my side here for x. That means this is the 4 minus x squared. Or I can set it up 2, because it's 4 minus, that 2 has to be there. I can set it up so that the square root of 4 minus x squared goes here and x goes there. It doesn't really matter. So if I choose this one, I'm going to start setting up my trig identities, or my trig ratios. So I know that the, excuse me, I know that the tangent of my theta is defined as the square root of 4 minus x squared over x, because this is my quote y over my quote x. So I'm setting up my ratios based on x, y, r. Now my x's are not really x's, maybe it could be, it could not be. And then my cosine of my angle is going to be equal to, in this case, x over 2, and my sine of the angle would be the square root of 4 minus x squared over 2. If I were to have used this one, say this is the way I wanted to set it up, cool, then my tangent in this case would be equal to the square root of 4 minus x squared over x. My cosine of theta is equal to the square root of 4 minus x squared over 2. And then my sine of theta is going to be equal to the x over 2. Now, it doesn't really matter which one you choose. It doesn't matter if you choose this setup or if you choose this setup. Now, I'm going to tell you that I probably will choose this setup because when I do my derivative here, I don't have to worry about a negative sign because I have to take a derivative of one of these. And you're thinking, why do I have to take a derivative? Because this is kind of like a u-sub. It's kind of like a u-sub. We call this a trigonometric substitution. So I know if I choose this second choice, and I take the derivative of both sides, the tangent of theta is going to be the secant squared of theta multiplied by d theta. And if I take the derivative of the right-hand side, I'm going to be stuck doing the quotient rule, which is not going to be very pretty, so I'm just going to leave that. I'm going to say, yep, not my first choice. Now, if I take the cosine and I multiply both sides by 2, I'm going to get 2. The cosine theta is equal to the square root of 4 minus x squared. If I take the derivative of both sides, I'm going to get negative 2 the sine of theta d theta. And the derivative of the other side is going to give me 1/2 4 minus x squared raised to the negative 1/2 dx. I'm not liking that one either. And then I have my last one. My last one would be 2 the sine theta is equal to x. So that means 2 the cosine of theta d theta is equal to dx. Ooh, there's my substitution. So I have a replacement for dx. So I come over here and I go, cool, I can replace this dx with, what did I say it was? It was 2 cosine theta d theta. Now you're thinking, okay, well, now I've got the square root of 4 minus x squared, and now I've got 2 cosine theta. What else do I need to do? Well, notice I didn't just start out with let u equal something of x. I actually started out with setting up all of the trig ratios, sine, cosine, tangent, based on the way I drew my triangle. Now, if you notice, let me erase this. before I took the derivative here, I said, wait a minute, this is 2 cosine theta is equal to the square root of 4 minus x squared. Ooh, there's my replacement in terms of theta. So this can be replaced with 2, the cosine of theta. So let me erase this. That was just for our setup to decide how we want it. What I really have in terms of my integration with the trig substitution is 4 because of this 2 and this 2. And I have the cosine squared of theta d theta. Now it's just a nice power reduction formula. And you're like, that was never nice the first time, but it's kind of nice. I mean, it is kind of nice. So let me erase this. I'm probably going to regret erasing it because I do have to back sub at some point because this is a substitution, so that means I have to back sub. So then this is going to be equal to 4, and then I have the power reduction formula for cosine squared, which is 1/2, 1 plus the cosine of twice my angle, d theta. Let me just have my brackets match. I'm going to multiply that 4 through, and so I'm going to get the integral of 2 plus 2, the cosine of 2 theta, d theta. And I have the integration, nice easy integration, so this is going to be 2 theta. And then the only way I got 2 cosine 2 theta is if I would have started out with the sine of 2 theta plus c. Now you're thinking, wait a minute, how am I going to go back to x's? Well, this is equal to 2 theta, that's not a problem. The sine of 2 theta is 2, the sine of theta, the cosine of theta plus c. And you're still like, how am I going to go back to x? And I told you I was going to regret erasing that. Remember how I set this up? I said this is theta. This was x. This was the 4 minus x squared, and this was 2. I said that the sine of theta is x over 2, so this gets replaced with x over 2. I said the cosine of theta is equal to the square root of 4 minus x squared all over 2. So 2 cosine theta is square root of 4 minus x squared. So this 2 and that cosine gets replaced with the square root of 4 minus x squared. And then you're like, okay, well, we got that replacement for sine and cosine. What about theta? Well, I have an infinite number of choices. Well, I don't really have infinite. I have 3 choices. The easiest choice, by the way, is to take this sine theta is equal to 2x and solve for theta. If I take this sine theta and solve for theta, I take the inverse of both sides, I'm going to get theta is equal to the sine inverse of x over 2. Now, could I have done that for cosine or tangent? Sure, I could have done it for any one, but that's the easiest one because it's the least amount of writing. So this gets replaced here with the sine inverse. My final answer is 2, the sine inverse of x over 2, plus x over 2 multiplied by the square root of 4 minus x squared plus c. And that is my final answer. Let's take a look at another one. And before I do that, I do need to erase. So I'm going to pause it now and erase a bunch of stuff. Let's take a look at my next example. Once again, I am going to set up my triangle. Now, in this case, I'm going to set up my triangle. Remember on my first one, I had options. I'm going to set the 2 here. And I know, again, that this represents r squared minus either x squared, or it represents r squared minus y squared underneath the square root. This time I'm going to set it up so that I have the, still the 2 is still going to be the hypotenuse, or the r, because I prefer r. This time I'm going to put my x here, and I'm going to put my square root of 4 minus x there. Now, if all of that's true, let's start setting up my trig functions. I typically just list them all out. So I start out with a sine of theta is equal to my y value, which is the square root of 4 minus x squared, over my r value, which is 2. Not my first choice to do derivatives. My cosine of theta is going to be my x value over 2. That's probably my preferred one to do derivatives. And then my tangent is going to be equal to my square root of 4 minus x squared over x. Now remember, I have to do derivatives, so I'm going to write this as 2 cosine theta is equal to x. I always choose the trig function that has x isolated with one step, which is multiplying both sides by whatever my r value is. So that's how I'm going to do that one. Now I'm ready to do derivatives. So I'm going to take the derivative of the left and the right, and I'm going to get negative 2 the sine of theta d theta is dx. So now I have my dx replacement. This gets replaced with negative 2 the sine of theta d theta. And similarly, I'm going to take this and I'm going to solve for the square root. And so I'm going to have 2 the sine of theta is a replacement for 4 minus x squared. So I'm going to go over here. I'm going to replace this with this 2, excuse me, 2 the sine, 2 the sine theta, 2 sine theta. Now, you're thinking, what? Where am I now? Well, this dx gets replaced with negative 2 the sine of theta, d theta. And then my denominator gets replaced with 2 the sine of theta. So you can see that this cancels down into just negative d theta. Nice. I freaking love this integration. This just becomes the negative theta plus c. Cool. Now here's where we have to back sub. So I come over here and I need to choose which one is going to be the easiest to solve for theta, and the easiest one to solve for theta is this one. So theta is equal to the cosine inverse of x over 2. And I come back over here and I say, okay, let's back sub. So this is going to be equal to the cosine inverse of x over 2 plus c. Don't forget you need a negative out front. And there's my final answer. Once again, I can see that I have 1 minus x squared, so I'm going to get ready to set up my triangle. Now my constant, which is the 1, is always going to go in, if it's the constant minus the variable squared, my constant is always going to go in the radius position. So this is going to be 1. I'm going to go back to writing this as being the square root of 1 minus x squared and this being x. Even though my quote x here is really the y position, I just like to take derivatives of sine better. I don't have to worry about negatives that way. So once again, I'm going to get ready to set these up. And so I do the sine of theta. This is where theta is. The sine of theta is going to be x over 1. Ooh, isn't that lovely? I'm loving that. So it's just going to be x over 1. That means I can go right to doing the derivative of sine, which is going to be the cosine of theta d theta, and the derivative of x, which is going to just be dx. So I got a replacement right here, which is the cosine of theta d theta. Cool. I also need to write all the rest of them out. So I have the cosine of theta is going to be equal to the square root of 1 minus x squared over 1, which tells me the cosine of theta is equal to the square root of 1 minus x squared. Cool. I have a replacement for here. That replacement is just going to be the cosine of theta. All right. But I also have x squared. Well, let me go ahead and square this side and square this side. Now I have a replacement for the x squared. Let me erase this. And so here, come over here, this integration becomes the cosine of theta d theta over my denominator, which is the sine squared of theta. And then my replacement for the square root is going to be the cosine of theta d theta. You notice that the cosines cancel, and so I end up with the integration of 1 over the sine squared theta d theta. And this is equal to the cosecant squared of theta d theta. And that gives me the negative cotangent. So this integrates into the negative cotangent of theta plus c. Well, over here I didn't have cotangent listed. So how do I back sub? Well, I can find cotangent. I know that the cotangent of theta, cotangent of theta is going to be my square root of 1 minus x squared, because that would be the equivalent of, quote, my x value over my y value, which is x. So now I have that replacement. So then this just becomes the square root of 1 minus x squared over x plus c, and that is my final answer. Let's take a look at ones in which I have the a plus the number or a minus number. This means I have the equivalent of x and y, and I'm solving, and I have the r that is missing. So to do these types of integrations, we go ahead and still set up our triangle. Boom, here's our triangle. And it doesn't matter where you put the x, it doesn't matter where you put the y. I'm going to put x here. Because this is of the form x squared plus y squared kind of form, then I'm going to put the 3 there. Because it is 9, that means 3 needs to go there. Now my radius then would be the square root of x squared plus 9. So now it's a matter of writing out my trig identities, or my trig ratios again. Starting out with a sine of theta is 3 over the square root of x squared plus 9. Not my first choice. The cosine of theta is going to be equal to x over the square root of x squared minus plus 9. Not digging that one. The tangent of theta is equal to 3 over x. I could live with that one. I'm not excited about that one either. The cotangent, though, of theta is equal to the x over 3. That's my choice. So if I multiply both sides by 3, I'm going to get 3. The cotangent of theta is equal to x. Now I'm ready to do derivatives. So I have negative 3, the cosecant squared of theta, d theta is equal to dx. So now I have a replacement, and let me see what else. So notice how all of these are sine or cosine or tangent. And notice that my variable is not really nice. So let's do the cosecant. So the sine of theta, the cosecant of theta is the reciprocal. So that means that I have the square root of x squared plus 9 over 3 would be the cosecant. So that means the cosecant of theta is equal to the square root of x squared plus 9. So now I have all my replacements using all those ratios. Okay. We know the x squared plus 9, this integration, the square root of x squared plus 9 gets replaced with 3, the cosecant of theta. We know dx gets replaced with negative 3, the cosecant squared of theta, d theta. And so what I end up with at this point is the integration of negative 9, the cosecant cubed theta, d theta. Now, get yourselves comfortable. I'm going to talk about what I'm going to do. I'm not going to go through the entire thing. But what I would do at this point is I would rewrite this as the integration. I'm going to bring the 9 out. Then you'll leave the negative in there. I'm going to rewrite this as the cosecant squared theta multiplied by the cosecant theta, d theta. The reason I'm going to do this is I have the 9, the integration. Cosecant, so I have a minus. I'm going to write this as the cosecant of theta. Cosecant squared can get replaced with the cotangent of theta plus 1 d theta. Now you're wondering why I'm doing this. Well, and then don't forget the squared, cotangent squared. I have 9, the integration of negative cosecant theta, cotangent squared theta, minus the integration of the cosecant of theta. Keep wanting to not put that c there. Cosecant of theta d theta. Now, what I did there is I distributed the cosecant on the cotangent squared and on that positive 1. And make sure I don't drop my 9. And then I separated it because I'm allowed to separate it. Now, we know from yesterday what this would be, that we know that this integration would have to have some sort of multiplier here of something like, I'm going to multiply by the cosecant of theta plus the cotangent of theta, numerator and denominator. And the reason I would do that is because I don't have that integration. So just look at the video from yesterday. That will take care of that. For this one, I'm going to integrate by parts. So a good choice for you would be the cotangent of theta. And you're thinking, wait a minute, cotangent squared, why am I using a cotangent squared? Well, I would rewrite this as a negative cosecant of theta multiplied by the cotangent of theta multiplied by the cotangent of theta. The reason I would do that is because I know what the integration of that is going to be. So that would be a good choice for DV. This is a good choice for you. Now I'm going to do this by integration by parts, and when I get totally done by the integration by parts, I'm going to get something that looks like this. It would be, when I get totally done, it's going to be negative 1/2, the natural log, negative 9/2, excuse me, the natural log of the absolute value of the cosecant of theta plus the cotangent of theta, and then minus 9/2. And I end up with the cotangent of theta, the cosecant of theta. I cannot do cosecant today. Man, so cosecant theta, and then plus c. I did all of that. And by the way, I'm not done because I have to go back and back sub. Everything needs to go back in terms of sine and cosine, or excuse me, x's and r's and y's and 9s and 3s. So I have a replacement for cosecant that is the square root of x squared plus 9/3. So this then gets replaced with a square root of x squared plus 9/3. The cotangent, if we come back over here, our cotangent gets replaced with x/3. And so my final answer when I get done is going to be negative 9/2, the natural log of the absolute value of the square root of x squared plus 9/3 plus x/3 minus 9/2. The cotangent, which it gets replaced with x/3. The cosecant, this gets replaced with the square root of x squared plus 9/3 plus c. I can do a little bit more cleanup, but pretty much that's my answer. And you wonder why trig integration is the best. Well, there's the best. Now, the difference between, say, this one and this one is, first of all, look where the square root is. And second of all, notice that it is 9x squared. Once again, I'm going to set up my triangle. And I'm going to put 3x on this side, and I'm going to put 1 on this side, and this becomes a square root of 1 plus 9x squared. I'm going to start again by setting up my trig ratios. And so I know that the sine of theta, because this is theta, is going to be 1 over the square root of 1 plus 9x squared. Probably not going to use that one when I do derivative replacements. I know that the cosine of theta is going to be 3x over the square root of 1 plus 9x squared. Probably not going to use that one. And then I have the tangent. Now the tangent is going to be 1 over 3x. So as before, I'm probably not going to use tangent. So I'm going to use the cotangent of theta, which is going to give me just 3x. Multiplying both sides by 1/3, I have 1/3 the cotangent of theta is equal to x. And now I'm ready to do my derivative. 1/3, negative 1/3, the cosecant of theta, d theta is equal to my dx. So now I have a replacement. This dx is going to be replaced with, this dx, man, I'm not ready to do that one yet. This dx is going to get replaced with negative 1/3 the cosecant of theta squared, d theta, so don't forget to square it down there. And let me erase this because it's kind of getting all muddy again. The square root part, notice how the sine of theta, notice the sine of theta is equal to 1 over. So this 1 over the square root can get replaced with just sine. So then this becomes the integration of negative 1/3 the sine of theta. That's a replacement for 1 over the square root. So that's kind of nice. Let me erase this. And then it's going to be multiplied by the negative cosecant squared of theta d theta. Now cosecant squared of theta is 1 over sine squared. So then this becomes, and the double negatives make it positive, so this becomes the sine 1/3, I'm going to bring that 1/3 out. The sine of theta multiplied by 1 over the sine squared of theta, d theta. So this equals 1/3. Well, this is integration of 1 over the sine of theta, d theta, which is going to give me 1 over 1/3 the integration of the cosecant of theta, d theta. And if you remember from yesterday and just the one I just did, we know that this is going to be 1/3 the natural log of the absolute value. Oh, I need to pull out a negative too. Don't forget to pull out the negative. So it'll be negative 1/3 the cosecant of theta plus the cotangent of theta plus c. And then don't forget to go back and substitute in the appropriate cosecant and cotangent in terms of x, and then we're done. We have one more of these, and then we'll look at when we have to complete the square and the joy and fun of that one. So once again, I'm going to set this up by, I'm just going to erase this. I'm going to set this up by setting up my triangle. You don't have to do it this way. There's other ways. If you like the way that you've seen in one of the other videos that I posted, or the way that you see in the book, by doing it in this form, totally fine to do it that way. I prefer the triangles. It just makes sense to me. I'm going to set it up this time. Now remember, I see the 1 plus x squared. I'm going to set it up this time so the x is here and the 1 is here. And this is going to be the square root of 1 plus x squared. Normally I put x in the x position, but this time I don't feel like it. So I'm going to set up my ratios. A sine of theta, here's where theta is going to be x over, a sine of theta is going to be x over the square root of 1 plus x squared. The cosine of theta is going to be equal to 1 over the square root of 1 plus x squared. The tangent of theta, this is just going to be x. Oh, that's kind of nice. I'm going to take the derivative of both sides. The derivative of tangent is the secant squared of theta, d theta, is equal to dx. So this gets replaced with the secant squared. So this gets to be replaced with the secant squared of theta, d theta. Now I need to have 1 over the square root of x squared. Well, if I square this side and I square this side, then this becomes the cosine squared of theta is equal to 1 over 1 plus x squared. But that doesn't quite replace it. So then if I square this side again and I square this side again, then what I'm going to get is I'm going to get the cosine to the 4th of theta is equal to 1 over 1 plus x squared, the quantity squared. Now I've got a replacement. So this over 1 is going to get replaced with the cosine to the 4th of theta. So where am I? Well, let me erase this so I can do this integration with those trig substitutions. And so I have the integration of the dx gets replaced with the secant squared of theta, d theta. 1 over 1 plus x squared, the quantity squared, gets replaced with the cosine to the 4th theta. Now, the relationship between secant and cosecant, well, secant, or cosine and secant, secant squared is the cosine squared of theta multiplied by the cosine of the 4th of theta d theta. This then becomes just integration of the cosine squared of theta d theta. And they're like, oh, this is the power reduction formula. That is true. It is 1/2, 1 plus the cosine of twice the angle d theta So just when you thought, oh, I don't have to do trig sub, oh yeah, trig sub is here as well as trig integration. And then I'll let you to that one, and don't forget to back substitute. So then what happens when I have x squared minus a squared? Not really much. Again, here is one of the ways that you can do it. I was doing it by the triangle. This is still kind of by the triangle. Notice how they set theirs up. This is the fact that I can replace x with secant, a secant. I'm totally fine if this makes more sense for you than doing the triangle. I'm totally fine with that. I don't care. It's whatever is the most appropriate for you to understand. So I'm not going to do these. These are a bunch of the repeating of the same thing. Let's look at these. And the reason I want to look at these is because if I take a look at, say, this one, I don't have anything yet, and this is why we started out with completing the square. So if I rewrite this by completing the square, so 1 over, complete the square, I'm going to have x squared minus 6x plus something, and then I have to take that something back off. So this is x minus 3, the quantity squared, because I would add 9 here, subtract 9, I have it, so minus 9. So this becomes x minus 3, the quantity squared, minus 9 dx. Now, it's in this section because we could do this by trig substitution. And if we did this by trig substitution, because it's something squared minus something else squared, then the triangle that I would build would be, my radius would be x minus 3, x minus 3. And one of the sides would be 3, the other side would be the square root of x minus 3, the quantity squared, minus 9. So once again, I'm going to say the sine of theta, this is where theta is going to be equal to 3 over the x minus 3. The cosine of theta is going to be the square root of x minus 3 squared minus 9 over x minus 3. And the tangent of theta is going to be equal to 3 over the square root of x minus 3 squared minus 9. Now I'm going to take this first ratio and I'm going to rewrite it in terms of x being in the numerator, because I know I'm going to have to put it in the numerator anyway. So I'm going to rewrite this to say, instead of sine, I'm going to use the cosecant of theta is equal to x minus 3 over 3. That means 3, the cosecant of theta, is equal to x minus 3. Excuse me. And then if I add 3 to both sides, 3, the cosecant of theta plus 3 is equal to x. Now I can do my derivatives of both sides. So I have negative 3, the cosecant of theta. Man, let me erase that. That is awful. For some reason, I just can't do cosecant right now. So I have negative 3, the cosecant of theta, the cotangent of theta, d theta, is equal to dx. So now I've got my dx replacement, which seems kind of awful. However, in my denominator, I have the x minus 3, the quantity squared, minus 9, which looks a lot like my tangent. If I divide both sides by 1/3, I'm going to get 1/3 the tangent of theta is equal to 1 over the square root of x minus 3, the quantity squared, minus 9. Now, if I squared both sides, I square this and I square this, I'm going to get 1/9 the tangent squared theta is equal to 1 over the x minus 3, the quantity squared, minus 9, which gives me a nice replacement. And so this integration becomes the integral of my 1 over x minus 3, the quantity squared, minus 9 gets replaced with 1/9 the tangent squared of theta. My dx gets replaced with, what was it, -3, the cosecant of theta, cotangent of theta, d theta. And then I'm going to replace tangent squared is 1 over the cotangent, so this becomes 1/9. Oh, multiplied by that 1/3, so that becomes a -1/3. The cosecant of theta. Tangent is 1 over the cotangent squared of theta. So I end up with cosecant over the cotangent of theta, d theta. I'm going to turn everything in terms of sine and cosine and see where I am. So this is -1/3. The integration cosecant is 1 over the sine of theta. Cotangent, 1 over the cotangent is tangent, which is the sine theta over cosine theta, d theta. And so this becomes -1/3. The integration of 1 over the cosine theta, d theta, which is -1/3. The integration of the secant of theta, d theta. Oh, we've seen this a million times. So this becomes the natural log of the absolute value of the secant of theta plus the tangent of theta plus c. And then don't forget to back sub. So that's that one. And pretty much all of these are going to be similar to what I just did. We're going to start with completing the square as needed. Some of them are going to be a little bit easier, like C should be a little bit easier, but that's pretty much it for this video. It is a long one, so enjoy, and we'll talk about it in class tomorrow.